Hi, I'm Laur Fisher from the MIT Environmental Solutions Initiative, and this is Today I Learned Climate. Here in the United States, the large majority of new energy that we're building today is clean, renewable, and doesn't pollute the climate. And mainly, that's thanks to two technologies, solar panels and wind turbines. They provided around 2/3 of new electricity in the U.S. in 2022.
We are gradually switching to putting up renewables as opposed to gas and other fossil fuel options because it's cheaper. The problem is we know we can't keep going at this pace without storage.
That's Professor Asegun Henry. He studies energy storage in the MIT Department of Mechanical Engineering. And he told us about how all of this new wind and solar is changing how we operate our electric grid.
Maybe this is something that people don't appreciate, but the way the grid operates is you have grid operators that try to do a prediction of how much electricity they expect everyone to use in the next hour. And then they effectively send a signal to all these power plants to tell them how much electricity to produce to try to match the load that they expect. And they do this very delicate 24/7 balancing act. If they make too little, the grid goes down. We're talking about switching to a system that right now is largely based on fossil fuels to a system that is based on renewables. And the big difference is that fossil fuels, it's like a faucet. You can turn up how much fossil fuels you use or turn it down and you have control over it. The same is not true with renewables. You do not get to turn a valve. You just get the weather that you happen to get that day.
And this actually is a major difference.
The upper ceiling on the amount of wind and solar you can deploy before you run into some serious problems is in the range of 20 to 30%.
Okay, hang on. Let's repeat that. In some parts of the world, their electric grid today, with no other technology, can only include 20 to 30% wind and solar energy and still be reliable. This is mostly because we need electricity when the sun isn't shining and the wind isn't blowing. But the opposite is true too.
So in places like California, Nevada, they're producing so much that they can't use it during certain times and they throw it away.
If we want wind and solar to be our main sources of electricity, we have to figure out a way to have more control over it. Energy experts call this issue intermittency because the energy output from wind and solar is intermittent. And that means we need a second technology to go alongside our solar panels and wind turbines.
You have to have some way of storing more energy than you need when the weather is favorable so that you can use it when the weather is not favorable.
So how exactly does energy storage work? What storage technologies are out there? And how much energy storage do we need to make wind and solar dominant? To answer those questions, we'll start at the beginning. Like the very beginning, one of the most basic laws of physics.
And the first law of thermodynamics basically says that you cannot create or destroy energy. But there are different types of energy, and you can convert between them.
So when we talk about storing energy, what we really mean is changing the form that that energy takes. So for our wind and solar intermittency problem, that means taking an electric current, turning it into something else, and then turning it back into an electric current later. Often that something else is chemical energy, the energy that holds together the atoms in a molecule.
Probably everybody's used a AA or AAA battery. There's one side of a battery that has one chemical. There's another side of the battery, there's another chemical. And these two chemicals really want to chemically react. And if they react, there's a lot of energy that's going to come out. You don't allow them to react, though. You instead put in between a separator material. It's called an electrolyte.
These chemicals might be different from one battery to another. A AA battery uses a zinc-based chemistry, while the more powerful batteries in a phone or an electric car are based on lithium. But the electric grid is much bigger than a phone or a car.
So when you now say grid scale energy storage, the number one thing you're talking about is the scale is huge. And so the amount of energy we're talking about, the amount of material, the size is dramatically different. And as a result of that, the way you think about what technology you would even use for that scenario is very, very different.
So instead of a phone, let's think about a power plant. A mid-sized coal, gas, or hydropower plant might produce around 500 megawatts of electricity.
If you wanted to store the amount of energy coming out of that power plant for 1 hour, that means your battery would have to be 500 megawatt hours.
For comparison, a very big non-grid battery, say the one that powers a Tesla electric car, holds roughly 100 kilowatt hours.
So 5,000 Tesla batteries is essentially what you would need. It's like half a football field. That's now getting to a scale relevant for the grid.
And that's just to store 1 hour of electricity from a mid-sized power plant. And we actually do store energy this way today. Facilities basically like the one that Professor Henry just described are being built and operated right now, especially in places with lots of renewable power like California, Texas, and Arizona. These facilities have thousands of large lithium-based batteries, and they solve a very specific problem.
What we do right now is we want to use batteries to smooth the transition between relying on a significant amount of solar during the day when the sun is out. The sun goes down, all that solar is going to turn off, and you have to ramp up fossil turbines to keep the grid going to compensate for it.
But those turbines, the ones that turn coal and gas power into electricity, they weren't built to turn on in the short amount of time that it takes for the sun to go down. Ramping them up that fast wears them out.
What you want is a battery that can help smooth it so that the turbine doesn't have to turn on super fast. That's a 1 to 6 hour battery that helps solve that problem. That's the first set of batteries that are being deployed now.
So this helps us get to a 20 or 30% wind and solar powered system, about where Texas and California are today. But beyond that, our storage needs actually change.
As you put more and more renewables on, now you got a different problem, which is I got to survive through the night on just renewables. So you need a battery that can charge up during the day and then keep discharging through the night until the sun comes back up. That's actually the majority of the batteries you need on the grid to do this kind of daily cycling.
We also need storage that can hold even more electricity than that.
There's going to be days where it's pretty cloudy. You don't get much sun. And these batteries are holding enough energy to keep the entire grid going. Then you got to even solve another problem, which is you may have an entire week or two where it's really bad and there's not much energy going out from the renewables, and you've got to have some reserve capacity waiting in the wings. These batteries may only turn on 4 or 5 times a year.
So how much energy storage do we need altogether for all of these different purposes? Well, estimates vary, but a U.S. government report in 2022 concluded that the U.S. alone, to get all of its energy from clean energy sources, including a high percentage of wind and solar, would need 6 terawatt hours of energy storage by 2050. That's the equivalent of 12,000 power plants or 60 million Tesla car batteries. Now, you could come up with scenarios that need less storage by relying more on other non-climate polluting sources, like maybe nuclear or fossil fuels with carbon capture and storage, or by building big transmission lines that move wind and solar power to where we need it the most. But even in those scenarios, we're still building a massive amount of energy storage in the future. And that's really only going to be possible if that storage is a lot cheaper than it is today.
All the cost targets for storage are about getting the storage cost so low that you can add it to the renewables. And so that means you need a 10 times cheaper battery than we have today. So now the two together become comparable or cheaper than gas.
Which is why researchers are trying to make batteries with different, cheaper, more common materials.
Iron, zinc, magnesium, aluminum, these are the cheapest elements on Earth. There's like a handful.
Iron and aluminum-based batteries, among others, have already been made to work in the lab, including here at MIT. But they're not ready for prime time yet. It's also possible that the future ultra-cheap energy storage we need won't look like a traditional battery at all. For instance, believe it or not, The main way that electric grids around the world store energy today is through water, with a technology called pumped hydro.
The way pumped hydro works is you have two bodies of water that are at two different heights. And to charge it up, you take a water pump and you move the water uphill.
And then when you need electricity, you let the water flow back downhill through the turbine in a hydroelectric dam. Today, more than 90% of the world's grid-scale storage is pumped hydro. It's cheaper than lithium batteries, and it can discharge the electricity slowly over a long period of time, making it good for the kind of long-term energy storage that we need most. But the issue is, it's hard to build more pumped hydro than what we have now.
It turns out that most of the good locations are already used up.
Well, here's an option that can work almost anywhere: hydrogen. In our 4th season episode on hydrogen, we talked about how you can use electricity from solar and wind farms to get hydrogen out of ordinary water. And then later, you can burn that hydrogen as a fuel to make electricity again.
Hydrogen, or fuels in general, have the ability to sit without any leakage. They'll be stored for extremely long periods of time and stockpiled.
And then there's a technology that Professor Henry works on: thermal energy storage.
So to charge a thermal battery, you now are taking in electricity and you're using it to heat up the atoms in an insulated box that doesn't allow that heat to leak back out. And then later, when you want electricity back, you allow them to cool down and you convert the heat to electricity, essentially in a similar way that we do in a power plant.
And there's also compressed air and superconducting magnets and all different other ways that scientists are getting really creative about storing energy in different forms. Which is great, because we will likely need several different options here. We might use one technology, like batteries, for the overnight problem of the sun going down, and quite a different option, say hydrogen, for the occasional dark, windless week. And as much as this sounds like only a technology problem, it isn't.
It is a bit frustrating that we treat technology as the only aspect of the problem where new things can happen, where new innovations can take place. People don't really get excited about changing a policy, but that's the bigger impact. I would say the Inflation Reduction Act and other new legislation has made this the most exciting time in climate technology development that we've had from a government funding standpoint. It's never been this good. It is undeniably a game changer for the companies and the technologies that need to get developed and deployed here.
That's our show today, but to learn more about energy storage and the technologies that might provide it, check out our show notes or our educator guide to bring these ideas into the classroom. That's all at tilclimate.mit.edu. And hey, I would love for you to email me. Yeah, you. Email me and the team at climate@mit.edu. Tell me about yourself and where you're listening from and why you listened to Today I Learned Climate. We would love to hear from you. And we may mention you and your work in a future TIL Climate episode. TIL Climate is produced by the MIT Environmental Solutions Initiative at the Massachusetts Institute of Technology. David Lishansky is our editor and producer. Aaron Krol is our writer and associate producer and did our artwork. Michelle Harris is our fact checker. Sylvia Scharf is our climate education specialist. Ilana Hirschfeld is our production assistant. The music is by Blue Dot Sessions, and I'm your host and producer, Laur Hesse Fisher. Thanks to Professor Asegun Henry for speaking with us, and thank you for listening.